Hey everyone, I hope you're all doing well and you're excited as I am to further our understanding in geometry, moving away from congruent triangles, and now we're going to talk about similar polygons. But before we get there, let's take a look at this example. So if you don't know what a bonsai tree is, it's basically a shrunken version of a real tree. And in this example, we're going to take a full-size tree, which is 118 feet, and compare that with this bonsai tree that is 15 inches tall. So in order to do that, we find a ratio or a proportion. But what do we notice here? Our bonsai tree is in inches, while our senator tree is in feet. Before we begin, we have to convert one of these units to the other so that we can have similar units to compare them to. So we do know that there are 12 inches in a foot, and in order to convert them, it's 118 feet over 1 times 12 inches per foot. That gives us 118 times 12, which happens to be 1,416 inches. Now, we have to write our ratios between the two trees. And hopefully you remember what a ratio is. If not, we're going to get into the formal definitions very soon. But the ratio between the two trees is 15 inches to 1,416 inches. If we simplify that, we can break up the 15, 3 and 5, and 3 and 472, and have a reduced proportion of 5 over 472, which gives us a ratio of the height of the bonsai to the full-size tree, which is 5 over 472, or 5 to 472. Now, if you're wondering why this is significant, well, my scale factor is 5 over 472. And if you remember our lesson in dilation, we essentially shrunk this 115-foot tree down to 15 inches. If you wanted to check your work, you would simply take the 118 feet, multiply that by your scale factor, and that would be 1.25 feet. In order to scale it down into inches, well, we know that there are 12 inches in a foot. And this will give me my 15-inch bonsai tree. So if you wanted to scale another tree down that it has a different height, you can do that with the same scale factor. So now for some definitions. So at this time, I'd like you to take a look, write this down in your notebook. Right now is a perfect time to pause the video and hit resume as soon as you are finished, and we'll discuss each one of these. Great. So a ratio. It is important to note that b cannot be 0 because that is in my denominator, and I cannot start the division process when I have a 0 in the denominator. Here are 3 different ways to write a ratio. I've used 2 of these and stated this last one as I spoke. Similar figures, well, 2 figures that have the same shape but not necessarily the same size. So again, if you think about our dilation, we started with a triangle, multiplied it by a scale factor to reduce my triangle. These figures are similar but not congruent. So if you recall, similar figures are similar if and only if there is a similar transformation that maps one figure onto the other. Essentially what I just said in my scale factor. Similar transformations preserve angle measures. So that means that this angle is congruent to this angle, while this is congruent to this, and all 90-degree angles are congruent to itself. Now let's take a look at corresponding parts of similar polygons. Right now is a good time to write this all down in your notebook. Pause the video, come back as soon as you're done. Great. So corresponding angles are congruent. As you see in my diagram, angle A is congruent to angle D, angle B is congruent to angle E, angle C is congruent to angle F. And if we have a similarity transformation that either enlarges or reduces my figure, like I stated in the previous slide, we multiplied it by a scale factor of k. So going from the left triangle to the right, we multiplied it by some scale factor k, in which case it's k times a, k times the side length c, k times the side length of b from the previous triangle. So corresponding side lengths are proportional. Basically, everything you see down here. While all corresponding angles are congruent. This is very important to what we're about to see. So, in the diagram on the right, we see that triangle RST is similar to triangle XYZ. And I'm asking you now to identify the scale factor from the first triangle to the next. And if you remember, the scale factor is the image divided by the pre-image. And we know that RS corresponds to XY. So we have RS and XY. That gives us 12 divided by 20. Reduce this for a scale factor of 3/5. Taking a look at the other angles, the other sides, we can see that we definitely have a similar triangle because every scale factor is equal to the same. Now, time to list all pairs of congruent angles. And we see that angle R is congruent to angle X. Angle S is congruent to angle Y. And angle T is congruent to angle Z. To write a ratio of corresponding side lengths in a statement of proportionality basically looks like this. 3/5 is equal to 3/5, which is equal to 3/5. Basically saying if all the sides are proportional, my triangle and my angles are congruent, my triangle are similar. Now let's take a look at how we do this. So we know that in this diagram, triangle JKL is similar to triangle PQR. I'm asking you to find the scale factor from triangle JKL to triangle PQR. So what does that mean? Well, I want to go from the pre-image to the image. This is important because our scale factor is the image divided by the pre-image. So let's take a look. Choose a different color. That means that our image, PR, is divided by our pre-image, JL. And that is 12 divided by 8, reducing this down to 3/2. You would do this for all three sides, and you would notice that you do get a scale factor of 3/2, which also means that my corresponding angles are congruent, and therefore I have a proportionality statement as this. So, corresponding lengths in similar polygons. If two polygons are similar, then the ratio of any two corresponding lengths in the polygon is equal to the scale factor of the similar polygons. Huh? Let's take a look with an example. So here I'm saying that triangle DEF is similar to triangle MNP. And in order to find the side length, I have to use the definition that I have above. So let's take a look. Since these two triangles are similar, the corresponding lengths are proportional. So that means that MN divided by DE is equal to NP divided by EF. Now I'm going to substitute my values as so, and I'm going to cross multiply to get 18x is equal to 15 times 30. I'm going to divide 18 on both sides to get x is equal to 25. So x is equal to 25. Great. Here in this diagram, I have triangle TPR is similar to triangle XPZ. I'm asking you to find the altitude of PS. If you don't remember, the altitude is the height of the triangle. So I'm asking you to find the height of triangle TPR sorry. So what I first have to do is find the scale factor. And the only lengths I'm given are the lengths TR and XZ. But since I know that they're similar, I'm going to set up a proportional statement. So I know that TR over XZ are corresponding sides. And so I have my scale factor of 3/4. Just like I did with the bonsai tree in the first example, I'm going to use this scale factor to identify my amplitude of PS. So PS over PY is 3/4 based on what I calculated here. And I only know PY, so I will substitute 20 for PY and solve for PS by cross multiplication. And it turns out that my PS, or the altitude of this triangle, is 15 units. Now, let's take a look at this. I'm asking you to find Km, given everything else. And notice that Jm is congruent to Ml, and GH is congruent to EH. So I'm going to use that to make my statement, which is GE over JL, which is 80 over 96, which reduces to 5/6 as my scale factor. Now, I'm going to do the same exact thing in order to find Km. I have FH divided by Km, and I know what the scale factor should be, which is 5/6, or the proportion 5/6. And I do know that FH is 35, as so. And again, I will cross multiply one more time to get 210 is equal to 5 times line segment KM divided by 5, and I get that KM is equal to 42. Now let's take a look at how to find the perimeter of two similar polygons. We'll use an example of a pool and an Olympic-sized pool. So an Olympic-sized pool has a length of 50 meters and a width of 25 meters. And the new pool that's going to be made is going to have a length of 40 meters. Now before we begin, we have to understand one little thing, and that is the perimeters of similar polygons. So if we have two polygons that are similar, then the ratio of their perimeter is equal to the ratio of the corresponding side lengths. So the perimeter, if you remember, is just the sum of all the sides, and that's what we have here in blue and in red for this one. And the perimeter is equal to the ratio of their corresponding sides, which can be either of the one. So let's put this into practice. So the new pool, all we know is that the length will be 40 meters, and that this new pool is similar to an Olympic pool that you see above. So the scale factor is the ratio between the lengths, which in this case is 40 divided by 50, or 4/5. And we know that the perimeter is equal to 2 times the length plus 2 times the width. And so let's find the perimeter of the Olympic pool, which is 150 meters. Again, that is 25 plus 50 plus 25 plus 50. Now, we can set up our perimeter of similar polygon theorem, which is x divided by 150. X in this case is the perimeter of my new pool. And 4/5 is the scale factor between the lengths. Again, I'm going to cross multiply to get that x is equal to 120. So that means that the perimeter of an Olympic pool is 150 meters and the perimeter of the new pool is 120 meters. This saves us a lot of time than applying the scale factor to both sides and then manually calculating the perimeter. Now, let's take a look at how to find the area of similar polygons. Here we have, if two polygons are similar, then the ratio of their area is equal to the square of the ratio of the corresponding sides. Basically, PQ divided by KL squared is equal to the area of the shaded region in red divided by the area of the shaded region of this quadrilateral. Now let's apply this. I want you to find the area between these two similar polygons. In the diagram, triangle ABC is similar to triangle DEF. Find the area of DEF. Given that the area of triangle ABC is 36 centimeters squared, or squared centimeters. Before we begin, the equation is up on the top right for your reference. And then we know that because the two triangles are similar, the ratio of the area of ABC to the area of DEF is equal to the square of the ratio of AB to DE. We're using AB and DE because that is the only information that we're given. So again, the area of triangle ABC divided by the area of the triangle DEF is equal to AB over DE squared. We're going to substitute the values and solve for the area. Now let's apply this. I want you to find the area between these two similar polygons. In the diagram, triangle ABC is similar to triangle DEF. Find the area of DEF. Given that the area of triangle ABC is 36 centimeters squared, or squared centimeters. Before we begin, the equation is up on the top right for your reference. And then we know that because the two triangles are similar, the ratio of the area of ABC to the area of DEF is equal to the square of the ratio of AB to DE. We're using AB and DE because that is the only information that we're given. So again, the area of triangle ABC divided by the area of the triangle DEF is equal to AB over DE squared. We're going to substitute the values and solve for the area. 10/5 squared is 100 over 25. So I'm going to cross multiply to get this, divide by 100, and get the area of DEF is 9 squared centimeters. 10/5 squared is 100 over 25. So I'm going to cross multiply to get this, divide by 100, and get the area of DEF is 9 squared centimeters. And that's it. I hope you found this video helpful, and congratulations for completing one of the few lessons on similar polygons. Bye!